Hi, everyone. I am Doug Dow here with Chegg for live office hours. We're going to be talking about some probability and statistics. And I'm here to answer all your questions. And we're going to try to work through some fun problems and talk about some probability and statistics questions. A little bit about me. I'm a PhD student at NYU right now, and my focus is in probability. I love the subject. I think it's super fascinating, and statistics is super useful for lots of things. So yeah, I hope we can learn a lot today. So feel free to drop any questions in the chat, and I'm happy to help you out and answer any questions. To get things started, I thought that we would go over. I have some questions. So one question I wanted to start off with is this sort of combinatorics question. So this is a classic um, uh, probability type of question, talking about decks of cards. And let me get my cursor going. Let's see. Here we go. Okay, so a classic set of questions in probability and statistics has to do with poker and decks of cards, and so it's nice to get used to these types of questions, and they're just kind of fun questions to think about. So if people aren't familiar with a 52 card deck, the deck has 4 suits, so clubs, diamonds, spades, and hearts, and each one of those suits has 13 cards, two up to ace, so that comes out to 52 cards. And we're going to just start with a couple questions about these type of decks. So let's say I randomly shuffle this deck. So I put it in a random order, and then I draw 5 cards. So we have these 5 cards. If you've ever played a card game or poker or anything like that, you might be familiar with these sorts of questions. What I want to ask is this combinatorics question, which is, what's the probability that I get 4 of a kind? And what 4 of a kind is we have 4 of the same kind, so 4 twos, for instance, and then a card that can be anything. So it could be 4 twos. It could be 4 of anything. 4 jacks. Doesn't matter. 4 of anything, and then another card that doesn't matter. So what's the probability that we get a pattern like this? So the way that we're going to answer this, which is going to be the way that we answer a lot of these problems, is we're going to count. We're gonna do some counting. So the probability of the probability of 4 of a kind. We're going to write this as we're going to compute this by computing the number of ways to get 4 of a kind divided by total number of hands. So this is a common thing in these types of problems where the probability of an event, if things are uniformly random, like there's totally random, is just the number of ways you can satisfy that event divided by the total number of the total number of events. So the total number of hands that we can get in this case. So let's first do the denominator, because that's a little bit easier. So how many hands, 5 card hands of poker are there? How many hands can we draw? So, how many hands? Ooh. So, if you've taken a probability class, you'll recognize this type of question. This is how many. This is another way to ask this is how many 5 cards can we draw from 52 cards? And here we're going to compute that without replacement. Without replacement. So maybe I'll give you a few seconds to think about it. If you try to remember, try to remember what this is. So I'll give you maybe about 10 seconds, and if anybody in the chat has it or wants to guess what it is, go ahead and put in the chat. I'll just give you about 10 seconds. Think about it. 5, 4, 3, 2, 1. Okay. Well, if you got it, it's going to be 52. Oh, I got. Yep. Yeah, exactly. Yeah. 52 choose 5. I got that from TikTok. Nicholas Miller got it exactly right. 52 choose 5. So this is, if you've seen this, if you've taken a class in this is a notation that might look familiar. Just for those of you who maybe haven't, I'll just write out what it is. It's 52 choose 5 is 52 factorial divided by 5 factorial times 52 minus 5 factorial. So that's the total number of hands without without order. Here I said replacement, but without replacement actually is right, and ordering doesn't matter. So that's the key thing here is like we're assuming these two things. We're not replacing the cards. We're not keeping track of the ordering. This is the total number of hands that we can get. So just a brief reason this is true. Well, the top is if you look at let's see, it's a little bit too thick. If you look at this 52 divided by 52 minus 5 factorial, that's going to come out to 52 times 51 times 50 times 49 times 48. So, and then we don't have any of the other numbers because we're dividing by 52 minus 5 factorial and then divided by 5 factorial. So we have 52 ways to choose the first card, 51 ways to choose the second card, 50 ways for the third card, and so on. So we multiply all of these different choices that we have. Each of these is the number of choices we have when we're drawing the hand. And then we divide by 5 factorial because that's the total number of rearrangements of the hand, because order doesn't matter. Okay, so let me know if you have any questions about that or want to go into that more. I'm gonna assume that we're roughly familiar with this going right now, but just if anybody wants to go into that a little bit more, just let me know in the chat. But yeah, great job. So that's the total number of hands. So let's do the numerator, which is a little bit harder, a little bit trickier. Let me just put that down here. Number for a kind. So here again, without replacement and order doesn't matter. So a lot of people get confused about when we take into account ordering and when we don't take into account ordering. When we're computing a probability like this, you can take into account ordering or not. It's okay, it doesn't matter, as long as you do the same thing in the numerator as you do in the denominator. So if in the denominator you're counting the hands with ordering, you have to do the same in the numerator. And the same thing if you're not counting the ordering in the denominator, you also shouldn't count ordering in the numerator. So that's sort of what we're doing here. And often in these like poker problems, you don't care about ordering of the hand. Ordering of the hand usually doesn't matter. So yeah, let's see. This is a little bit trickier. Let's see. Maybe if anybody wants to think about the answer, maybe I'll give you a similar amount of time. So what's the probability of getting 4 of a kind? Let's try to think about it at home a little bit. So again, to just describe what 4 of a kind is, we need to get 4 cards of the same kind, and then the other one can be anything. And here I've written it, in a specific order. Again, let's just do it without ordering. Order doesn't matter. So, yeah, why don't I'll give you all about maybe 10 seconds to try to think about this. If you can get it, great, and try to post in the chat. It's okay if you're wrong. This is a little bit trickier. So, yeah, don't worry about that. So let me just give you about 10 seconds. So I'll just wait here a little bit. See if anybody has any ideas. Okay. 5, 4, 3, 2, 1. Okay. Okay, so wait, let me see. Okay, so from TikTok, a user said, is it 48 times 13? So that is a great answer, and it is correct. So yeah, that's great. Great job. So yeah, that was from TikTok. Looks like user did some numbers. So yeah, great. So yeah, so let's walk through that. So the way to think about this, the way that I like to think about it, is in terms of how many choices do you have to construct this hand. So first, so it's like how we did up here. We counted how many choices are you able to make. So let's think about how many choices we have in making a 4 of a kind hand. So first, I'm gonna think about choosing the 4 of a kind. And there are, in this 52 card deck, there are 13 different kinds of cards. So there's 13 choices, and I choose one. Right? So it's 13 choose 1 is the number of choices I have for the kind. And I'm gonna, so that's the first choice. And then we say, okay, we've made that choice. And then we go forward and say, what other choices do we have? So typically we're gonna multiply the first, the number of choices we have here times the number of choices we have after that. And so once we've chosen the first 4 of a kind suit, how many other choices do we have? Well, there are 48 cards remaining because we've already chosen 4 of them to be in the hand. And we only can choose one of those to be in our hand. So we have 4 of this suit. So let me write some things. So 4 of a kind choices. And this is the last card. And this comes out to 13 times 48. Yeah, awesome. And so to wrap this up, if we go back up here, this probability of getting 4 of a kind is the number of ways to get a 4 of a kind, which is 13 times 48, and then divided by the total number of hands, which is 52, choose 5. So I we don't really have to simplify this right now. Often it's totally fine if you just leave it in this sort of times 52 5 factorial. So I'm just going to leave it like this right now. Often you can just write it like this. If your teacher wants you to actually get a number, then you plug these numbers into your calculator, use the factorial function, or use Desmos or whatever you like to use. It'll come out to something very small. So typically for things like this, we don't even want to put it in decimal because it's just going to be a very small number, and so it's easy to make rounding errors and everything. So it's a little bit nicer to have it in this form anyway. Awesome. So that's cool. Good job to everybody who got that right and participated. So yeah, awesome. So now you know, next time that you play cards, you'll know what the probability of getting 4 of a kind is. Awesome. So yeah, so next I wanted to do another sort of the next step with this. Also, if anybody wants to, if you're just joining now, this is the Chegg Probability and Statistics office hours. I'm a math PhD in probability, and I want to answer your probability questions and help learn together. We're doing some card counting problems to get used to some basic probability and counting problems. But feel free, if you have other types of problems you want to work on, if you have a specific, what's the probability of getting a full house or anything, what's the if you have any other question, feel free to shoot it over on any stream, and make sure to, and also follow Chegg on Instagram, TikTok, and YouTube, and Twitch. So let's do this question. So we already found the probability of getting 4 of a kind. Let's say next I flip over the first 2 cards, and it happens to be 2 kings. So I flip over the first 2 cards. I get king of clubs, king of diamonds. Now what's the probability of getting a full house? So the scenario is I get king, king, and I don't know what's under the last 3 cards. What's the probability of getting a full house? And for those who don't know these terms, a full house is the name for a hand that has 3 of a kind and a pair. So, for example, the following would be a full house: king, 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 and then let's say 2, 2. So that would be a full house. Another full house would be king, king, and 2, 2, 2. It doesn't have to be 2. It could be ace, ace, 3, 3, 3. So 1 pair and 1 3 of a kind. So it's a pretty nice hand. But once you get a king, once you get 2 kings, it's more likely, right? It's you already have your 2 pair, so you're already partway there. So let's try to think about this. Again, we're going to do a similar type of analysis. Probability of full house, giving 2 kings. So here we're gonna do the same thing. We're gonna count number of successful hands and divide by number of hands. So this is the common thing in these types of problems, if you want to find, we're randomly shuffling a deck, probability of some event is the number of ways it can happen divided by the total number of ways, of the total number of events. Awesome. So here, so let's do the denominator first. The denominator is typically a little bit easier. I should say hands left here. What we're gonna do is we're not gonna count all the number of hands because we've already revealed 2 kings, and so there's only 3 more cards left. And so we're going to count the number of hands given that we have 2 kings already. Okay. So let's see if we can get this this number. It's going to be pretty similar to what was said in the chat earlier, except a little bit different. So let's see if we can get this right. So again, we're not caring about replacement. We're doing this without replacement. Order doesn't matter. So how many ways can we fill in these 3 last cards? So I'll give you a little bit to think about it and post it in the chat. All right. 2, 5, 4, 3, 2, 1. Let's see. Oh yeah, okay. I'm seeing from from TikTok Potato is saying it's a nice name, by the way. I have a cat named Potato, so definitely fond of that name. We can get another king and a pair or a trio of anything. Yeah, that's great. Yeah, so that's really great. That's the sort of analysis we're going to do for the numerator. So let me just finish up. So that's sort of the what we're going to do for counting the number of hands. So that's really good. So you're actually 1 step ahead of me. So let me finish this number of hands. So the number of hands is just going to simply be 50. Choose 3, because we have 50 remaining cards. We've already drawn the 2 kings, and there are 3 choices. So it's simply that we have 50 choices. We have 50 possible choices, and we're choosing 3. And this is, ordering doesn't matter without replacement. Awesome. And okay, so now let's go back to what Potato said and use that analysis, use that idea to try to count the number of successful hands. So yeah, so there are 2 possible scenarios. Either we get king, king, and another king, and then 2 other, and then a pair, or we get king, king, and then 3 of a kind, right? So this is the 2 different scenarios. What I'm going to do to start this off is I'm just going to fix what the last type is. So what the last kind is. What I mean by that is it could either be a 2, a 3, a jack. Let's choose that. Let's count how many ways we can choose the last kind. So there are 12 possible remaining kinds of cards, and we're going to choose one of them. So that's 12, choose one. So that fixes whether this is a 2, a 3, a jack, whatever. There's 12 ways to do that because the king, we can't have the king. The king's already been chosen. So we've made that choice, and we're going to multiply by the number of ways given that we can then go ahead and fill in the rest of the hand. And just as Potato said, we're going to have 2 different options. So let me write this as number 1 plus number of 2, right? So 12 choose 1. So let's count the number of ways we can get 1. So this is, we get a king, king here. Okay, I'm going to draw a line here for the left is what we've already seen. The right is what we have to choose. So we're going to get another king, and then we're going to get 2 of the type that we've already chosen. So how many ways can we draw another king? Well, there are 2 kings left in the deck, and we're choosing one of them. And so I'm going to write that as 2 choose 1. Okay? So this is the king choice. And then we have to choose the 2 from the 4 um, of the other type of card. So we have 4 of, let's say it's 2s. We're going to choose 2. Okay, that's too many 2s. Let's say it's jacks. We're going to choose 2 jacks out of the 4 jacks in the deck. So the number of ways that the event 1 can happen, given that we fixed the second type, is 2 choose 1 times 4 choose 2. Okay. Let me know if you have any questions about that. It's this stuff, if you haven't seen it before, is always a little bit confusing. But I like to think about it as just counting the number of choices that you can make. Okay. And then we're going to add to that the number of ways we can do number 2. So how many ways can we do that? Well, we have already chosen the type. So let's say it's jack. We're going to choose 3 from the 4 jacks. So that's 4 choose 3. Okay. And there's no other choices. We just have to choose the 3 cards. So by that I mean, if it's confusing, there are 4 jacks in the deck, or 4 of that specific kind, and we're going to choose which 3 of them to include. Okay, and there's 4 choose 3 ways of doing that, right? And so let's simplify this a little bit. 12 choose 1. So 12 choose 1 is just 1. It's just just 12. I mean, just a fancy way of writing 12. 2 choose 1 is just 2. 4 choose 2 is, we're going to use this formula that some of you might have seen. It's 4 times 3. Made my 3 look funky there. 4 times 3 divided by 2 plus so that's 4 choose 2, and then 4 choose 3 is just 4. It's just 4. It's just 4. So, and the other way to see that is, if you're choosing 3 items from a group of 4, that's the same as choosing the one to leave out. So, and how many ways are there to choose the one to leave out? There's 4 ways, because there's 4 different guys to leave out. So that's going to be 4. We can simplify this a little bit. So this is 12 times, so 12, these 2's are going to cancel, plus 4. Okay. And this is, so 12 times 16. Cool. And so putting this together, our final answer is 12 times 16 divided by 50 choose 3. And if we wanted this in a little bit more, something that's easier to plug into a calculator, we get 12 times 16 on the bottom. 50 choose 3 is 50 times 49 times 48 divided by 3 factorial. And 3 factorial is 3 times 2 times 1, which is 6. So this is 50 times 49 times 58 divided by 6. So let's put this in here. And then the 6, we divide it by it, but then it comes up. So we have 6 up here. Awesome. Awesome. Yeah, great job, guys. Cool. So again, if you're just joining, this is the Chegg Probability and Statistics office hours. We just did a really fun poker type problem calculating probabilities of certain hands. So we just completed that. Let me know if you have any questions that you want to tackle. Just post them in the chat wherever you are, and I'm happy to talk through them, or any concepts that you want to go over. Feel free to post them in the chat, or just let me know how you feel about probability and statistics. What are your thoughts? What do you hate about it? What do you love about it? Um, awesome. So, uh, so we get another question. I'm gonna upload um, another question that I have prepared. Let me just go ahead and uh, actually, I guess I can just scroll down. There we go. That's good. Okay. So I'm just gonna upload. Let's see. I have combinatorics questions. I have expected value questions, variance questions, uh, statistics questions. Um, let's do. Okay, let's do a. So let me know if anybody has some topic that they want to go over. Just type it in the chat, and um, we can find something to talk about there. Let me zoom in a little bit. Okay, so this is another question that's sort of combinatorial, counting things. We call this like combinatorial problems because they're about combinatorics, about counting sets. And so yeah, so let's dive into this one. So this is we're going to so the question is, we're gonna imagine that we have uh, a bus with 5 seats, and there are 5 students: Dwight, Angela, Jim, Pam, and Michael, and they're randomly assigned to the seats. So we could have D, A, J, P, M. So they're randomly shuffled in the seats, and we're going to ask a couple questions about this. So Michael is concerned about being an outsider, and so he wants to know, what's the probability that he's going to get an outside seat. So by outside seat, I mean one of the seats where he doesn't have 2 neighbors. So does anybody have an idea about this question? I'll give you all a little bit to think about it. What's the probability that Michael's on the outside? So I'll give you maybe about 10 seconds. Just go ahead and post it in the chat wherever you are. Let's see how many answers we can get. I'll give you about 10 seconds to think about it. Okay. Oh, it looks like all right, thanks. So yeah, so from TikTok, I'm seeing Potato is answering either far left or far right. 2 over 5. Yep, that's exactly right. So yeah, so we don't have to do much analysis here. So the idea is there are 2 seats where Michael is on the outside, on far left or far left, and there's 5 total. And because everybody's jumbled around, there's 2 over 5 probability that he's on the outside. One way to think about this is, again, we're counting the number of ways he can be on the outside divided by the total number of positions. So that's one way to think about this. But yeah, so it's just 2 over 5. Okay, great. So let's see. Let's look at B. So Dwight and Angela kind of want to sit together. So they want to know, what's the probability that they're going to be able to sit together. So this might be relevant for, you want to, for you all. It's sometimes important to know what's the chance that you're going to sit next to some person, whether you like them or not. So let's try to think about that. So what's the probability that they're going to sit together? So this is a little bit more involved. So maybe I'll just go into this and do it and try to follow it along at home. And if you can think about it or try to think about how to do it on your own and want to post in the chat, go ahead. I'm just gonna sort of go through it. And so what's the probability that Dwight and Leonard sit together? I'm gonna do a little bit different analysis to what we've done so far. Before, we just been counting. So we're just counting the number of ways they can sit next to each other divided by the total number of ways they can sit. So we can totally do that. That's more that counting method. I'm going to do it a little more probabilistically this time. So I'm going to do the following. I'm going to compute the probability adjacent. I'm going to break it up into two different events. So there are following events. The first, this is a trick that we use a lot in probability, where to compute the probability of some event or the expected value of some quantity, we first condition on some event happening. And then we compute the probability conditioned on that event. So this is equal to the probability. This is called the law of total probability. What I'm going to do. The probability adjacent given A in seats in seats 2, 3, 4 times probability A in seats 2, 3, 4 plus probability adjacent. I just realized my pen's super light, so just a little bit. Okay, I think that's okay. Okay. Let me know if you're having trouble seeing, and I can. What about I zoom in a little bit? Okay, probability adjacent given A in seats 1 or 5 times probability A in seats 1 or 5. So, okay, it's a little bit long, but what I'm doing here is the following. I'm sort of looking at this event that they're adjacent, and the reason that I broke it up into these two different, I broke it up the event into these in this way is because if Angela is sitting in one of these middle seats, the probability that Dwight is sitting next to her is 2 over 5, because there are 2 ways that Dwight can sit next to her. Oh, sorry. It's 2 over 4, because there's 4 different ways there's 4 different options for seats that Dwight can be in, and 2 of them are adjacent to Angela. Right? So this is using the law of total probability, where I'm breaking up an event that's maybe complicated into individual events, distinct events that are that are easier to calculate the probability of. So if Angela is in seats 2, 3, and 4, the probability that Dwight is next to her is 2 over 4, which is 1/2. And then I multiply by the probability that A is in seats 2, 3, and 4, which, using it's the same reasoning as we did for the earlier question about Michael, that's going to be 3 divided by 5. Okay? So now we're going to tackle the next part of this formula here. So now we're going to go to the situation where Angela is in seats 1 or 5. So this is slightly different, because if Angela is on the outside, there's only one place for Dwight to be next to her, right? And so instead of 2/4 probability of being adjacent given Angela in these seats, it's only 1/4. The probability that Dwight is next to Angela given that Angela is in seats 1 or 5. Okay. And then we're going to multiply by the probability that Angela is in seats either 1 or 5, which is 2 or 5. That's the same thing that we did earlier with when we calculated the probability that Michael is on the outside. Right? So you see what we did here? We broke up this maybe a little bit complicated event of what's the probability of them like sitting together into these two different events that are a little bit easier to deal with. So yeah, let's simplify this a little bit. So this is going to be 6/20 plus 1/10, right? So and then this is going to be, so 6, put it over 10. This is going to be 3/10 plus 1/10, which is 4/10, which is 2/5. Awesome. Okay. Yeah, let me know if you have any questions about that and why we did what we did. So for those who sort of if you sort of understand what's going on here and want to try to test if you really understand, if you really get it, try to think about, what if there were 100 seats instead of 5? So okay, I got a message from TikTok from Potato. Can we also do 2 times 4 factorial divided by 5 factorial, like if we treat the couple as a block? Let me try to think about that. So it comes out to the same number. So let me try to think. Okay, so it comes out to the same number. So I'm sure it's correct. So if we treat this couple as the same block, let me try to think. So I think that's right. So I think what you're doing, I'm guessing what you're doing is you're saying you're doing a counting method. So you're counting the numerator. So can we what about, so 2 times 4 factorial divided by 5 factorial? So let me try to guess what you're getting at here, and I my intuition is that it's totally correct. And what you're saying, I think, is you're saying you're doing counting methods. So the denominator is the number of ways we can place these 5 individuals in the 5 seats, with ordering mattering. That's 5 factorial. So why does order matter here? Well, we're asking a question about that cares about ordering, right? We want to know whether 2 of the people are next to each other. So ordering matters. So that's right. And then you're saying, how many ways can I put Angela and Dwight next to each other in the numerator? Well, what I can do is I can treat them as one, big, Dwight Angela ball right here, kind of smush them together. Don't try that at home. And I'm going to place, and then I'm going to treat the other people as individuals, right? And there are 4 factorial ways to, let's see, I had Jim, I had Pam, I had Michael. There's 4 factorial ways to arrange these 4 objects, right? 3 humans and 1 sort of, I don't know what to So some, double human hybrid. So there's 4 factorial ways to permute them, the objects. And so that's where the 4 factorial comes from. And the 2 comes from the number of ways we can permute Dwight and Angela. So here, the way I've drawn it, it's sort of Dwight first, Angela second, but it could be Angela first, then Dwight second. And so for every single combination of, permutation of these 4, I can also permute these 2. So yeah, that sounds like a completely valid way to get to the same answer. And that's a great point, that often in these problems, there's many ways to get to the same answer. And so if you are confused about one thing that I'm doing, you can try it yourself, right? Whatever way feels the best to you. And sometimes one way will be easier, which is why it's nice to sort of get exposure to different ways. Yeah, so that's great. You could think about, like, how do you generalize this to, let's say, Dwight and Angela sitting together and Jim and Pam sitting together, right? What would you do then? Well, maybe you could consider Dwight and Angela as a block, and then Jim and Pam as a block, and then Michael. So, and then you're permuting, the number of ways that you can permute this is 3 factorial. And then for each of these blocks, Dwight, Angela, Jim, Pam, there are 2 ways to permute them. So 2 times 2. So that's the number of ways that we could arrange these 5 people so that Angela and Dwight sit together and Jim and Pam sit together. All right, I'm seeing from, yeah. Yeah. I'm not going to repeat that. Yeah, exactly. So, yeah, that's what Michael would say if you know this show. Yeah. So, yeah, and Michael is alone, unfortunately. Yeah. Sorry, Michael. Okay. So, but yeah. So, yeah. So you could then use that similar analysis to try to count the number of ways that you can do this. You can, permute these individuals. And then to get the probability of this event, you divide by 5 factorial. Awesome. Yeah, so if you're just joining us, this is the Chegg Probability and Statistics Office Hours. I'm Douglas. I love probability and love talking about it, and happy to field your questions. We got about 12 minutes left, it looks like, so we're not going to get through nearly the amount of questions that I have written down, but I'm happy to, if anybody has any questions that they want to go over, any topics, just go ahead and put those in the chat wherever you are. We can go through them. So let's until I get one of those, let's we can try to think about this question. What if this sort of extension to this question? What if there were 100 total seats in a row and 100 people, including Dwight and Angela, randomly assigned as seats? What's the probability that Dwight and Angela will sit together? So we can do, there are many ways to do this. We can go to, Potatoes method here. We could do the law of total probability, whatever way you like to. Maybe I will do the law of total probability just to wrap it into this so that we can see the comparison here to the 5-seat situation. So the idea is we compute the probability of adjacent is equal to, there's 2 events. Adjacent given A, adjacent given A in seats 1 to 99, and then times that probability. 2 to 99. And then plus probability adjacent given A is in 100 times probability A in 1 or 100. Here I'm using some shorthand. I hope it's not confusing, but let me know if it is. If you want some clarification, I'm happy to help. Yeah, so if A's from 2 to 99, again, there are two possible spots for Dwight to be in. So either Dwight is to the left or to the right. So there's two ways, and there are 99 other places for Dwight to be. And so that's 2 over 99 chance that Dwight is adjacent to Angela, given that Angela is in seats 2 to 99. And then the probability that Angela is in seats 2 to 99, it's just, there's 98 seats here out of 100. So it's just this. And then let's do the other one. So probability that Dwight is adjacent, given that Angela is in either 1 or 100, is there's one option instead of two. And then here, probability that Angela is in seats 1 or 100 is 2 over 100, because there are 2 seats there over 100 total. So now we just put this all together. Let me see. Let me take out a 2 over 99. I'm just going to simplify this a little bit. So 98 over 100 plus 1 over 100. That gets us 2 over 99 over 99 over 100, which is 2 over 100. So you might be able to, the next thing is what if instead of 100 it's n? So that's the next thing that you can think about. The maybe the hint is it's going to be 2 over n. Try to show that. So yeah, that's great. So yeah, so that just shows that there's, for a lot of these questions, there's many ways to do it. So it's kind of fun. There's a lot of different possibilities to how you want to solve these questions, right? Okay. I'm trying to look for a last problem. First, I guess we can also just get to this. What if they're, instead of a row, they're in a circle? So that would be, so that's something that maybe you can think about at home as well. If you have the answer, go ahead and put it in the chat. I'm going to maybe, just so we can get to some other question, I'm going to go ahead and try to get to the last question that we're going to do today, probably. So let me go ahead and get that up here. Okay, so I thought this is kind of a fun one. So the question here is about Powerball. So so let's say a Powerball lottery ticket costs $2, and after buying the ticket, you select 5 distinct numbers out of 69 and write them down on your ticket. And if your 5 numbers are the same as the 5 numbers randomly drawn by Powerball, you get $1 million. This is roughly how very simplified version of how Powerball works. Obviously it's a little bit more complicated in real life, but it's a little bit just a simplified version. The question is, what's the expected value of buying this ticket? So let's try to think about this. So we haven't done an expected value question so far this office hours, but let's just try to get through it. This gives you a sense of, is it worth it to buy it, right? If it's negative, it's generally not worth it to buy it. So let's think about this. So the expected value, let's say X is the winnings of the ticket. So we want the expected value, let's say, of ticket. We want the expected value of buying a ticket is X minus 2, because we already we have to pay 2 for it, and so we if we don't get anything, we just pay 2. We get with negative 2. So we want the expected value of this. So I'm going to use this trick called linearity of expectation that allows us to write expectation of x minus 2 as expectation of x minus 2. And now we should calculate the expectation of x. So the expectation of x, in this case, is there are only 2 possible values of x, either $1 million or $0, right? So the expectation is going to be 0 times probability x equals 0, which is just 0, right? And then plus 1 million, which is 10 to the 6, times probability that x equals 10 to the 6. This is how you calculate an expected value. If you have more values that x can take, you're going to have more terms in this sum. So to answer this, let's calculate the probability that you win the $1 million. So the way that this is set up is you choose 5 numbers from 69. This is, I believe it's actually similar to this. So, and if your 5 numbers match the drawn numbers from Powerball, then you get 69 choose. Then you get the million. You get $1 million. So it's obviously very simplified. Don't take my word for it. So what's the probability that you choose the right 5 numbers? Well, similar to what we were talking about at the beginning of this session, there are 69 choose 5 ways to draw 5 numbers from 69 numbers total. And you have to choose, there's only one correct answer, right? And so the probability that you choose the right 5 numbers is 1 over that. This comes out to about 8.9 times 10 to the negative, I believe it's 10 to the negative 8. So if we plug that in here, this expected value is 10 to the 6 times 8.9 about times 10 to the negative 8 minus 2. This comes out to about, so this is 10 to the 6 times 10 to the negative 8. It's going to be 8.9 times 10 to the negative 2 minus 2. Okay, we can see where this is going roughly. This is going to be, this is about 0.089 about minus 2. So it's about equal to negative 1.91 about. So negative. Okay, so I guess the lesson there is that typically it's not a good idea to buy these tickets, but and we can justify that with expected value and probability. So that's one reason that it's useful in the real world. You get some rigorous mathematical justification for this, and that's what that's why it's important. So yeah, awesome. So we're coming to the end of the Chegg probability and statistics office hours. It's been lovely chatting with you all, and I've had a great time doing these problems, and I hope you come back next week at the same time we'll be doing this. And also there's a ton of other really great Chegg office hours. You can follow the you can scan the QR code to keep up with the schedule, and follow on YouTube, Twitch, Instagram, and TikTok to catch these office hours. And yeah, I've been really hope you keep learning and loving probability and statistics. So and yeah, I think that's about it for today. So yeah, it's been great, y'all.